Hello and welcome back. In this video, our goal is to find the intervals for which the function is concave up and concave down and any possible inflection points. So to do this, we want to start off by finding our derivative because we need to get our second derivative. So for finding our derivative, we need to use the quotient rule. So we're going to have 1 times x squared minus 4 minus x times 2x divided by x squared minus 4 squared. And we want to simplify this derivative down before we go ahead and take a second derivative. So that's going to be x squared minus 4 minus 2x squared over x squared minus 4 squared, which simplifies down to a negative x squared minus 4. And that's going to be divided by x squared minus 4 quantity squared. All right, so the next thing we want to do is go through and find our second derivative, once again using our quotient rule, but this time also the chain rule. So our second derivative is going to be with the derivative at the top, which is negative 2x, times the bottom, which is x squared minus 4 squared, minus the numerator, negative x squared minus 4, times the derivative of our denominator, which is going to be 2 times x squared minus 4, times the 2x by the chain rule. And now this will all be divided by x squared minus 4 raised to the 4th power. Now you'll notice in this derivative that we have some common factors that we can eliminate as part of the simplification process. In particular, we've got an x squared minus 4 common to both of our terms in our numerator. So we can cancel out this x squared minus 4 here, cancel out this extra x squared minus 4 to have 1 left. And down here, we'll have 3 x squared minus 4s. So now cleaning this up, our second derivative is going to be negative 2x times x squared minus 4. And then we're going to have plus x squared plus 4, because I'm distributing that negative into that factor, times a 4x, all over x squared minus 4, now raised to the 3rd power. And we can distribute and combine like terms and do more simplification here. So let's do that. Multiplying out, we're going to have a negative 2x cubed plus an 8 times x plus a 4 times x cubed plus a 16 times x all over x squared minus 4 cubed. And we can combine like terms. And that'll leave us with, let's see here, we're going to have 2x cubed. And then we're going to have plus 24x over x squared minus 4 cubed. And we can factor the second derivative. And that'll take us to a 2x times x squared plus 12 divided by x squared minus 4 to the 3rd power. All right, so now we need to go through and study this second derivative. And you'll notice that it's only equal to 0 when x is equal to 0. So we'll take note of that off to the side. F double prime of x is equal to 0 when x is equal to 0, because a fraction can only be 0 when its numerator is 0. X squared plus 12 is always positive, so that leaves 2x to be the only thing that could possibly equal 0, which makes x equal to 0. So what we need to do now is draw a number line and label all the points where we have our second derivative undefined or equal to 0. So let's draw a number line for our second derivative. And we're going to have, first of all, the point 0 on there, because 0 is where our second derivative is equal to 0. But we're also going to have positive 2 and negative 2 on this number line. So we'll put a undefined symbol there because our second derivative is undefined at 2 and negative 2. However, they cannot be inflection points because our original function f of x is not defined at plus or minus 2. Okay, so the next thing for us to do is to test out the second derivative in between these places where the second derivative is 0 or undefined. So the first value we'll start off with is going to be positive 3. And you'll notice that if we look at f double prime of 3, it is going to give us a positive value because 2 times 3 and 3 squared plus 12 is a positive numerator. And then 3 squared, which is 9, minus 4 cubed is positive as well. So f double prime of 3 is greater than 0. So our second derivative is positive on this interval here. The next number for us to test out is going to be positive 1 because that's between 0 and 2. And if we substitute 1 into our second derivative, you'll notice that we have a positive numerator, but we have a negative denominator. So f double prime of 1 is less than 0. So we have a negative second derivative between 0 and 2. Next up, we can calculate the second derivative at negative 1, which is between negative 2 and 0. And if we use negative 1, you will notice that we get a positive second derivative because our numerator is 2 times negative 1 times something positive, so it's a negative quantity. And down below, negative 1 squared minus 4 is negative. 2 to the third power is still negative, so that is going to be a positive second derivative at negative 1. So we'll label those with positives. And you can kind of imagine what happens left of negative 2. If we use negative 3 in our second derivative, we have a positive denominator, and we're going to have a negative numerator because 2 times negative 3 is negative 6. Times something positive is going to be a negative number. And again, down below, negative 3 squared is 9, minus 4 is positive. So that's going to be a negative fraction. And so now we know that left of negative 2, we have a negative second derivative. Now remember, we're looking at concavity here. So we actually have concave down from negative infinity to negative 2, concave up from negative 2 to 0, concave down from 0 to 2, and then concave up again from 2 to infinity. So we're going to be concave up on negative 2 to 0, union 2 to infinity. We're going to be concave down on the interval from negative infinity to negative 2, union 0 to 2. And you will notice here that we don't have an inflection point at negative 2 because we are undefined there, so there's no point on the graph. However, we do change concavity at 0, and 0 is in the domain of the original function. So that function value actually ends up being 0. So we know that the point 0, 0 is an inflection point. Because again, it is on the graph of the function, and it's a location where the concavity changes from concave up to concave down. So we've done a full analysis of our second derivative, and we now know when our function is concave up and concave down.